So in recent times, there are two methods to meet the demand for accelerated and high performance for numerical simulations of chemical kinetic systems. The first method is the physics-informed neural network, and the second method is about operator learning. The advantage of physics-informed neural network is the integration of physical laws into the loss function and the data efficiency. But the disadvantage of physics-informed neural network is the challenges in the training process, because the training is very difficult when we integrate physical laws into the loss function, and the customizability for specific problems. For operator learning, the advantage is that we can learn map between function spaces, and it is applicable to different settings. And today I will only focus on one method in operator learning. So the definition of operator learning is that the operator learning is to learn a function operator. It is mathematical entities that map functions from one space to another. We can apply operator learning in solving ODEs and PDEs. The advantage of operator learning includes efficiency, flexibility, and generalization ability. For the methodology part, first we should write PDE in the form of operator. In the first equation, your AU represents an operation acting on the column vector X. And the second equation shows the initial or boundary conditions. The solution can be written in the form of kernel if we use the green function method to construct a green function G. Drawing insights from this integral representation, the architectural network structure is constructed as shown in the third equation. Fourth equation. Expressed in neural operator, the whole structure of operator can be simplified as the final equation that we use K to represent the integration operators as shown before. To effectively address the integration in the kernel function, a pivot method is introduced that is Fourier neural operator, which is shown here. Then the part of the integration operator can be replaced by Fourier transformation and the inverse Fourier transformation. The semantic diagram is shown below. That we get our input vector and pass them to the encoder and pass them to the Fourier layers, and finally get the output vector. Box call transformation, a statistical technique, serves as a fundamental tool in data pre-processing to rectify skew distributions and stabilize variance. In our problems, we employ BCT to handle data of concentrations or mass fractions in chemical kinetic systems. Flowing the ideas from the BCT maps these low-order quantities to O1 magnitudes, thereby addressing the singularity issue in logarithmic transformation when data approaches values near zero. The advantage of BCT relies on its adaptive nature. That is, by analyzing and optimizing the transformation parameter lambda in BCT equation, it offers a tailored adjustment to align data with the assumption of normality. Also, when training the FNO model, it is better to include physical information along with the data, since we know all the details of the chemical kinetic systems. More specifically, integrating the information of ordinary differential equations into the neural network can ensure the physical properties and maintain good generalization ability of the model. In this way, the element conservation loss and the mass fraction sum loss are added in our loss function correspondingly. And the equation is shown here. So during complex reacting flow simulations, the reaction zone may be confined to a specific area. As a result, most of the sampling points are located in areas where thermophysical states are constant, leading to unbalanced sampling points. can cause the loss function to be distributed in a unbalanced manner, so that the training process is biased by the focused data points. To tackle this issue of a skewed loss function due to the sampling imbalance, an approach is to divide all sampling points into several groups and introduce a weight factor into the loss function. Such a method can help balance the distribution of data samples in the loss function. Another way is to add a modulating factor to the conventional loss function. This factor is close to zero for accurately classified samples and approach for those inaccurate. In other words, it amplifies the weight assigned to inaccurately predicted samples in the loss function. And the whole structure of our extended FNO is shown here. And first, we have the input vector, and we pass it to the part of box call transformation. And we have the encoder and the decoder that encodes or decodes data into high dimensions. Fourier layers includes linear transformation and Fourier and inverse Fourier transformations. So then we get our output vector, and we will use this loss function to calculate the loss and finally optimize the parameters in our structure. And the second part is the model validation. First, we use some toy problems to demonstrate our model. Robot problem refers to the reaction equations shown below. The reaction rate constants vary in a range of 9 orders of magnitude, showing the stiffness of this ODE system. We obtain the dataset by randomly sampling a total of 12,000 initial conditions of chemical species Y1, Y2, and Y3. The range of initial conditions utilized to construct the dataset is presented in this table. Notably, the ranges of Y1 and Y3 in the testing dataset are beyond the range in the training dataset, which are intentionally designed to test the capability of our model to predict solutions for unseen initial conditions. This figure presented 100 sample initial conditions in the testing dataset and the temporal evolution of concentrations, as well as the prediction results from the trained model. From this figure, we can see that our model can not only accurately predict the results of the next time step, but also maintain a high level of accuracy when recursively predicting the results of subsequent time steps. This figure demonstrates the training and testing dataset distributions in Y1, Y2, and Y3 parameter space. It is seen that compared with the sampling data distribution in the training dataset, there exist data points in the testing dataset that lie outside the distributional boundaries of the training dataset. It is significant to show here that the testing solution trajectories in the parameter space do exceed the range of the training sampling data points. This indicates challenges related to generalization ability and model performance. Remarkably, the prediction results in last figure show a great performance of accuracy when facing with testing conditions lying beyond the training data set, which can demonstrate our model's generalization ability. The second problem is a pollute problem. Pollute problem is an air pollution chemical kinetic model with 20 species and 25 reactions. This system has this table displays the initial conditions range of representative chemical species in the training and the testing data set. The range of initial value in the testing data set again exceeds those in the training data set, specifically for species Y1 and Y4. And the following figure further shows 100 sample initial conditions from the testing data set, along with the corresponding predicted results. And the great performance has been achieved. So to further test the performance of our model, it requires more complex chemical systems than toy problems such as the robot problem. Therefore, our model is then examined with the chemical kinetic system of homogeneous autoignition, characterized by 7 chemical species and 16 individual reactions. To construct the data set, we randomly selected initial conditions covering a spectrum of equivalence ratios and initial temperatures, as outlined in the following table. First of all, we presented here two illustrative testing cases to show the prediction accuracy and our model's generalization ability. The plots of the temporal evolution of chemical species for these two illustrative testing cases are presented in the following figure, providing a visual insight into the performance and the predictive capacity of our model. Furthermore, the prediction performance of our model is compared with a uniform deep neural network. The DNA model consists of three hidden layers, each with neurons of 128, 256, and 128. And the activation function used in DNA model is LKIRU. Yeah, and our model holds a similar number of parameters for each species. So as shown in the next figure, results of these chemical species and in DNA model is failed to predict a very good performance, and our model can achieve better performance compared with it. Additionally, since one of the major extensions in our study is the inclusion of physical information, so we then compare the prediction results of our model with and without physics-informed constraints trained by the same dataset, as shown in the first figure. Our model with physics-informed constraints has shown a better performance than the model without physics-informed constraints. And in the next figure, we can see the result of the physical loss for the same case with and without physics-informed constraints added in the loss function. And we can see that when we don't add physics constraint into the loss function, our model shows a higher loss value than the one with physical constraints. Finally, we then evaluate the effectiveness of incorporating the box cause transformation into our model. Employing the BCT into the model enhances its capability to accurately forecast the evolution of small-scale chemical species. The comparison of predictive performance with and without employing BCT is depicted in this figure. Notably, some species exhibit worse prediction results when BCT is not applied. This is because BCT enables the model to more clearly capture small changes in species with magnitudes of low orders. Then come to the conclusion part. So in our study, Fourier neural operator is extended to learn stiff chemical kinetics by imposing physical constraints and reformulating loss functions. Experiments indicate that the extended FNO has the ability to extrapolate into untrained conditions. And our future work includes evaluating extended FNO with complex reacting flow cases and revise this structure to increase its ability to predict and generalize to unseen conditions. Also, our future work includes combined structure with chemical kinetic solvers in open form. Thanks very much.
Thank you. Thank you for the presentation. Any questions for this topic? Okay, go ahead.
Thank you. Hi, because my research did not involved with any chemical reaction, so I have a very simple question for you. I think you have a chemical reaction solver, and you're right, here it is. You mentioned that there are 20 species and 25 reactions in your research. Is that right? Okay, so did you develop a new solver for your research, or you just used embedded original solver in the open form? So the original solver can already to resolve such a really complex question?
Yes, and my object is to use the model to replace a part of my final object is to use this model to replace a part in the original solver.
Okay.
That is to predict the advance of the source terms. Okay.
Okay. Thank you.
Any more questions? Okay.
Thank you for your presentation. I have a question about the chemical mechanism. I've noticed that you validate the auto-ignition delay time, but I was wondering, have you tested about the laminar flame speed? Because both of them are the key parameters for chemical mechanism. So I was wondering if your methods can promise the mechanism you get from your deep learning model can suitable for both IDT and laminar flame speed.
Actually, in this problem results, if I only change the equivalence ratio and initial temperature for the problem, our model can only display the results for only these two chains, but not for other conditions.
Okay. I thank you for your answer. I think I can talk with you later.
Okay.
Hello, I want to know how large is your model,
and large is my model.
How can is your model? Can you model accelerate this calculation?
Acceleration. You mean the acceleration process?
Compared with the ODE solvers.
ODE solvers. I think the deep learning method is to accelerate the deep learning model is to accelerate the solver process, and I haven't compared our model with original solvers speed.
Okay, thank you.
Okay, thank you for your presentation again.